Hello students, today we are going to study a new topic, that is Fourier series. This is a part of unit 3 of your syllabus and we have already finished unit 4. So before starting with the new topic, let us first recall some of the basic definitions which we have already studied. So we are starting with the definition of periodic function. A function f is said to be periodic with period p if f of x is equal to f of x plus p. That is, the function f repeats itself after the period p. For example, sine and cosine functions are periodic functions with period 2 pi. If you look at the graph of cosine function, its curve in the interval 0 to 2 pi is same as the curve in the interval 2 pi to 4 pi, 4 pi to 6 pi and so on, because it is periodic in nature. So, for a periodic function, if we want to study its properties, we can study its properties in any of the interval, and since it is periodic, its nature is going to be same throughout the line. Next, we have the definition for even function. A function f is said to be even if f of x is equal to f of minus x. Means if you replace x by minus x, the function is going to be same. It is not going to change. For example, f of x equals to x square. If you substitute x as minus x, it is again x square only. One of the important properties or important characterization of even function is that its graph is always symmetric about y-axis. For example, if you look at the graph of f of x is equal to x square, you can clearly see that it is symmetric about y-axis. Next, we have the definition of odd function. We know that a function f is said to be odd if f of x is equal to minus f of minus x. That is, if we replace x by minus x, the function is going to be same but with a negative sign. For example, f of x is equal to x cube. That is an odd function. If you look at the graph of any odd function, then it is always symmetric about the origin. So please remember these characteristics because we are going to use these properties in this lecture of Fourier series. Here I have listed some of the formulas, basically integration formulas, which will be required throughout the lecture. For example, if you look at one, the integration of cos nx from alpha to alpha plus 2 pi, that is within an interval of length 2 pi, is 0 whenever n is not equals to 0. If you look at say 4, then the integration of sin mx cos nx within an interval of length 2 pi is 0 whenever m is not equal to n. For example, if we want to integrate sin 2x cos 3x within 0 to 2 pi, then we know that since m is not equal to n, its integration value is going to be 0. So we are going to use these formulas directly without computing them again and again. Let us now start with Fourier series. Fourier series are basically used in analyzing the periodic functions. It is actually the approximation of a function in terms of sine and cosine. In engineering, many of the phenomena are periodic in nature. For example, current and voltage in an alternating current circuit. So these periodic functions can be analyzed by a process called Fourier analysis. That's why we are aiming to find an approximation using the sine and cosine functions with the help of Fourier series. So the definition of Fourier series I have mentioned here. The Fourier series of a function f in the interval alpha to alpha plus 2 pi is given by f of x is equal to a0 by 2 plus summation n from 1 to infinity an cos nx plus bn sin nx, where these coefficients a0, an and bn are mentioned here. a0 is equal to 1 by pi integration alpha to alpha plus 2 pi f of x dx. An is equal to 1 by pi integration alpha to alpha plus 2 pi f of x cos nx dx. And Bn is equal to 1 by pi integration alpha to alpha plus 2 pi f of x sin nx dx. So if we are required to find the Fourier series of a function f, we are going to get these values a0, an and bn, and after getting these values, we are going to substitute it to get the Fourier series or Fourier approximation for a function f. Before going to an example, let us see how to compute these coefficients a0, an and bn. To find these coefficients, we are first assuming that the Fourier series, means the series given in the right hand side here, can be integrated term by term. So first we are integrating the Fourier series within the interval alpha to alpha plus 2 pi as mentioned here. So basically we have applied integration here from alpha to alpha plus 2 pi. So this becomes integration alpha to alpha plus 2 pi f of x dx is equal to a0 by 2 integration alpha plus 2 pi dx plus summation n from 1 to up to infinity an integration of cos nx dx plus summation n from 1 to infinity bn integration of sin nx dx. Now we know that whenever n is not equal to 0, integration of cos nx and integration of sin nx is 0. You can refer this here. Integration of cos nx and integration of sin nx is 0 whenever n is not equal to 0, and here in our formula the summation is running from n from 1 to up to infinity. So definitely this integration and this integration is going to be 0, and we are left with a0 by 2 integration of dx is x. After keeping the limits we get alpha plus 2 pi minus alpha. So alpha gets cancelled, 2 gets cancelled, and we are left with pi into a0. So from here we can get the value of a0. So the value of a0 becomes 1 by pi integration of alpha to alpha plus 2 pi f of x dx. So this is the value of the coefficient a0 which we have listed here. Next, we are required to get the value of an. If you look at the function given to you, an is 1 by pi integration of fx cos nx dx. So we first multiply the given approximation or the given Fourier series both sides by cos nx, and then we are going to integrate it from alpha to alpha plus 2 pi, which you can see here. So I have multiplied cos nx to both sides and then we are doing the integration. So the right hand side becomes a0 by 2 integration of cos nx plus summation n from 1 to infinity an integration of cos square nx plus summation bn integration of sin nx into cos nx. Now these integration values you can get from the table I have given to you. So this integration is 0. This integration is pi and this integration is 0 again. Please refer to the table and the formulas 1, 4 and 7 given here, because every time it will save some time of yours. You are not required to compute all these integrations again and again. So finally we got the right hand side as pi into an. From here we can get the value of an, which is 1 by pi integration alpha to alpha plus 2 pi f of x cos nx dx, and it is same as the value of coefficient given in our formula for Fourier series. You can get the value of the coefficient bn also. I have left this part for you. To get the value of Bn, you multiply the entire equation with sin nx and then integrate it from alpha to alpha plus 2i. Definitely you will get this formula. Please check it on your own. Now we are going to see one example for Fourier series. So the question is to find the Fourier series of the function f of x equals to x square in the interval 0 to 2 pi. So here alpha is 0. So this interval is alpha to alpha plus 2 pi. Since alpha is 0, the interval becomes 0 to 2 pi. We know that the Fourier series of any function is given by this formula. F of x equals to a0 by 2 plus summation n from 1 to infinity an cos nx plus bn sin nx, as we have mentioned in the Euler's formula for the Fourier series, where a0, an and bn are given by these formulas. So we have substituted alpha equals to 0 and the formula becomes a0 equals to 1 by pi integration 0 to 2 pi f of x dx. An is given by this term and Bn is given by this integration. So we are going to substitute f of x equals to x square and we are going to evaluate the coefficients a0, an and bn. So I have substituted f of x equals to x square. So the value of a0 is 8 by 3 pi square, you can check. Similarly, in the value of the coefficient an, I have substituted f of x equals to x square and after integrating I am getting the value as 4 by n square. For bn, I have got the value minus 4 pi by n. After getting the value of these coefficients, we are going to substitute these values in the Fourier series of the function. Substitute a0 as 8 by 3 pi square, an as 4 by n square and bn as minus 4 pi by n in this formula. So the resultant becomes f of x equals to x square. This is the given function which is equal to 4 pi square by 3 plus summation n from 1 to infinity 4 by n square cos nx minus 4 pi by n sin nx. So this is the Fourier series of the function x square, means x square is approximated with the help of sine and cosine functions. Here I have given one example so that you can compute the Fourier series of the function f of x equals to x square in the interval minus pi to pi. So here alpha is taken as minus pi. So the interval become minus pi to 2 pi. Again this is an interval of length 2 pi only. And after getting the Fourier series, you are required to deduce this equality. So when you will compute the Fourier series of this function x square in this interval minus pi to pi, you will get the approximation given here. X square will be equal to pi square by 3 plus 4 summation n equals to 1 to infinity minus 1 raised to the power n divided by n square cos nx. So this will be the Fourier series, that is the first part of this question. Next, you have to deduce this equality as well. You have to prove this part as well. So you substitute x equals to pi and you will see that you will end up in this equation. So please compute this example and let me know if you face any difficulty. Here I have given some more example. Try to complete these as well and we will take some more example in the next lecture.